Hello everyone. Previously, we've been looking at what happens when you take the limit on a function as x approaches infinity. So now we want to ask the question, what about if we are approaching some specific limit, where instead of it going towards infinity or negative infinity, what happens with the behavior of a function as x approaches some specific value? So this might be a problem like this. We have this velocity problem. Suppose you have a ball that's dropped from the upper observation deck of a tower 450 meters above the ground. How could we find the velocity of this falling ball? So we first have the function that's describing the distance of this free falling object, s of t equals 4.9 t squared. So basically it is the distance that the ball falls, and it is accelerating by some time t squared, right? So that would control how far it's fallen. Next, we have our average velocity, which is the change in position over the change in time, which can be written as the function at time 2 minus the function at time 1, so where it was positioned at time 2 minus where it was positioned at time 1, over the difference between time 2 and time 1. And then how do we define and find this instantaneous velocity, right? So what happens as it's approaching some specific point? Right? So just kind of draw a picture, an idea of what this would look like. You have some cliff here, you're dropping a ball off this cliff, and we're pretty much saying, okay, well, what is the average velocity where it is here? This would be position 2, so s t2, and let's say from the initial position here, which would be s at t1, right? How much has it fallen on average? And it would just be the change in position, which in this case is from here to here. It's just subtract, so take s at t2, subtract off s at t1, and you get the distance between those two positions, over the change in time. How much time did it take to get from position 1 to position 2? And this would give us our average velocity. On average, at what speed is this ball falling? Where the position of the ball was described by s of t is equal to 4.9 t squared. Now this would be an example of what we're talking about, where we want to see, we have some definite limit, right? There's some point where the ball is going to hit the ground. It doesn't go off to infinity. So we can have any point, at this point starting from time 0 up to the time where it would hit the ground, or position 0 to whatever distance, right? So the fact that we had that this cliff was 450 meters would mean that we definitely would not have this ball dropping into infinity. So the notation we're going to be using for this phenomena is much like what we did when x was going to infinity, is that we'll have the limit as x approaches some value a on our function f of x, and this will equal to L, whatever this limit would be. This means that our function f of x is approaching this L as x goes to whatever value a is in this case, whatever we're approaching. So this means we can make values f of x arbitrarily close to L by taking x sufficiently close to where x is not equal to a. So basically what we're doing is, let's say that a is here, and we want to know what's happening as we approach this a value. Well, we might take a value here, so let's say it's a1, and then maybe we get a little bit closer, a2, a3, and what's happening as we get closer and closer and closer to this value a where x does not equal to a. Now the reason this is important is because oftentimes we're going to have functions that we can't actually touch a, right? For example, we might have something like this where, let's say that your function looks like this, where neither side coming from the left or the right, where this would be minus, this would be plus. Neither of those can touch a because for some reason, whatever function this is, a is not an option. But we can look at what happens with the limit as we approach that point a, where in this case, because from the left, we're going off to infinity, from the right, we're going off to infinity, we could say that the limit on this function would be infinity. Now here on this slide, you can actually see a couple drawings to illustrate what this might look like. So in the first drawing on the left, we have some function that crosses through the point A, where we can take the limit as it approaches from both the left and the right, and also where it hits at that value A. And we will see that in this case, it's a continuous function because it approaches from both the left and the right, and it also intersects at that same point A. Whereas in the middle would show an example of a function where it approaches some value A from the left, it approaches some value A from the right, but at that point A, there's suddenly a jump. You see the dot below. This means that at A, it has a different value. Then we have the third image on the right, which represents some function where you can see as we approach from the left and we approach from the right, they're approaching the same value, but it cannot touch that value. This might be something like if you put this in the denominator of a fraction, it would end up making a 0 in the denominator. So in this case, it can be anything but that point. So in this case, it has what's called a hole, which means that there is a limit, right? From the left and the right, it does approach some value, but it can never actually touch that value. So what we're going to do when we look at the limit is we're going to look at what happens as we get sufficiently close to that value without ever being at that value. So let's look at some intuitive ideas of what this might look like if a function is convergent and if a limit exists and is a real number. So a function is divergent if there's no limit or if the function value approaches either positive infinity or negative infinity. So looking at these images, you can see on the bottom left, we have this function where it starts in the top left corner of the first quadrant and it moves downward as it approaches 0. So as x approaches infinity, you can see that this is converging down to 0. The second image shows an example of what a divergent function might look like. As x increases towards infinity, the y value is increasing exponentially up towards infinity. So in this case, it's diverging to infinity. The third image shows something where it might be some function where it is, in this case, going up and down. It's increasing, it's decreasing, it's increasing, it's decreasing. But each time it is shrinking and getting closer and closer and closer to some specific value. So in this case, as x approaches infinity, it's converging on some value. So in this case, we would say that it converges to some value L. So the limit as x approaches infinity is equal to L. And then the last image has points where it is at 0 and then up to some value. Let's say it's 1. So it goes from 0 to 1, 0 to 1, 0 to 1. In this case, it looks like it's not increasing or decreasing between those jumps. All that's happening is it's consistently jumping from one value to the next, back and forth, back and forth. This means that it's not converging, so therefore we would say this diverges as x approaches infinity. Now, a quick recap on how infinity works is that infinity is not a real number. So even though we will write the limit as x approaches infinity, f of x equals infinity, or as the limit as x approaches negative infinity, f of x equals, if you have it approaching some value infinity or negative infinity, we would say this function is divergent to plus or minus infinity. So since infinity is not a real number, not all operations will hold. We talked about this in the last lesson. If I can add infinities, right? Infinity plus more infinity would still be infinity. Infinity times infinity would just be infinity. But what does it mean if I have infinite objects or infinity and I subtract infinity from it? In this case, it doesn't really make any sense. So this would be undefined. Similarly, if I have infinity and I divide by infinity, this really doesn't make any sense either, so again, this would be an undefined outcome. Now, one approach you could take is, let's say that we have the limit as x approaches 1 on x minus 1 over x squared minus 1. Now, if we were to first test out plugging in 1 for every x value, what would we get? Well, 1 minus 1 would be 0. Divided by 1 squared is 1, minus 1 is 0. So we would get 0 over 0, which is undefined and specifically indeterminate. So one thing we could do is we specifically want to look at, okay, well, if we can't be at x equals 1, what would happen if we approach from the left, and what would happen if we approach from the right? So in this case, we're going to have two things we look at. The limit as x approaches 1, and we'll put a little minus sign, meaning we're approaching from the left, and this would be x minus 1 over x squared minus 1. We'll also be looking at the limit as x approaches 1 from the right, which would be a little plus sign, again, of x minus 1 over x squared minus 1. So we're going to be looking at what happens as we approach from the left and the right. Now, one method you could use is to use numerical analysis of this, where we're just going to say, okay, well, what if I plug in numbers and I get closer and closer to this value 1? and I see what happens. So we have an example of this where we might have our x values and then what is the outcome of our function at those x values. So for example, if we plugged in 0.99, our function outputs 0.502. If we plug in 0.999, getting closer to 1, we get 0.50025. If I plug in 0.9999, I'm going to get 0.50002. So looking at this, coming from the left side, as I approach a equals 1, it looks like as I'm approaching that 1, I'm getting closer and closer and closer to the value 0.5. Now, of course, we talked about if I plugged in 1, we don't know what's happening here, right? This is indeterminate, so we have no idea. So now let's look at what this function might be approaching as we approach from the right. So we're going to be a little bit bigger than 1. So let's say that in this case we do 1.0001, 1.001, and 1.01. So we'll do the same sort of operation. We're starting, fairly close, and we're getting closer, and let's see what happens. So at 1.01, if I plug this value into this function, I will get 0.49751. If I plug in 1.001, I would get 0.49975. If I plugged in 1.0001, I would get 0.49997. So what's happening as I approach from the right? Well, from the left, it appears that we are approaching 5. As I approach from the right, it also looks like we are approaching 5. So in this case, the limit from the left and the right is 5 for both of them. So we would say the limit as x approaches 1 is equal to 5. As we approach from the left, it's approaching the value 5. As we approach from the right, it's going to the value 5. Therefore, the limit as x approaches 1 will be equal to 5, even though we cannot plug 1 into this function. So we don't actually have a value there, but we do approach 1. So this would look something like we were talking about, where in this case, it's just a little above 5, this one's a little below 5. So it might look something like this, where this would be at x equals 1, right? We can approach this value from both sides, but we never actually can be that value. So now what we're going to do is we're going to look at it analytically to see if this matches. Now, one quick correction I want to make. I forgot to put my decimal here. So this, every time I said 5, it should have been 0.5, but not a big deal. The whole thing stands, right? It was going towards, it was 0.5002, 0.50002. The other one was 0.499. So these were 0.5. So now what we want to do is we want to see, can we confirm this analytically, right? Because a lot of times you don't really want to plug in a bunch of numbers because it's kind of tedious. And if we can just solve for it, then why wouldn't we? So I'm going to rewrite my limit here. We have the limit as x approaches 1, and this was x minus 1 over x squared minus 1. And we talked about the fact that if I were to just plug in 1 into each of these x's, it would be 0 over 0, which is undefined. So now what we're going to do is we're going to first split this into its separate components, right? We have x squared minus 1. So what we can do is we can actually change this to x minus 1 over, and the square of this would be x minus 1, x plus 1. Now you might wonder, how did I know to do this? Well, a lot of times your clue for a problem like this would be, if it looks like there's probably some connection between whatever's in the numerator and the denominator, and the bottom is, one of them is a square, then it probably is going to end up with some cancellation for a lot of these kind of calculus problems. So in the fact that I had x minus 1 up here, I was looking at this term here with the square and it's saying, okay, well, could this be some square terms, two terms multiplied by each other, that I just brought together into 1? So in this case, I just kind of basically figured it out by the fact that if I did x minus 1, x plus 1, I know that if I were to FOIL this out, I would get x squared, okay, good, minus x plus x, and then minus 1. So the plus x and the minus x would cancel, therefore it would leave me with x squared minus 1. So that looks good. So now in this case, because I have x minus 1 at the top and the bottom, the numerator and the denominator, I'm going to cancel these out, and I'm going to be left with the limit as x approaches 1, 1 over x plus 1. Now, if I were to plug in 1 at this point, what happens? Well, I take the limit of 1. This is just going to be, limit of a constant is constant, so this is 1. Plug in 1 to this, I get 1 plus 1 equals 1/2. Well, 1/2 can also be written as 0.5. So we've actually shown that this function does in fact approach 0.5 whenever we are approaching x equals 1, taking the limit as x approaches 1 for this function, right? And if we were to graph this, it looks something like this. Right, as x equals 1, we have that this is equal to 0.5. Sorry, it's open circle. And this would go off towards infinity. This would go off towards 0. And then we also have at x equals -1, we have something like this. And this is because if I were to plug in -1, -1 minus 1 would be -2, but -1 squared becomes 1. 1 minus 1, we'd still end up with a 0 denominator. So in this case, we actually have a point that we couldn't approach either if we were coming from the left or the right here. But the reason I wanted to show this is because in this case, we're not worried about the rest of this function. We're only looking at right around here where a equals 1. We're looking at what happens as x approaches from both the left and the right. So for our next example, we're going to be looking at the limit as x approaches 0. Now in the slide, you'll see that it says pi over x. This was actually a typo. It should have been sine of pi over x. So in this case, we're going to, again, see what happens as we plug in our different x values and what outcome we get for our function at that x, right? So we're going to be looking at x and f of x. So if I were to just start with 1, because I want to approach 0, let's start at 1 and we're going to move back towards 0. And let's say that I plugged in 1 here. I would get sine of pi over 1. So sine of pi, this is going to be equal to 0. Now let's say that instead I decided to do 1/2. I'm going to take half the distance from that. Well, if I take pi over 1/2, this is the same thing as saying pi over 1 divided by 1 over 2. You fractional division, this becomes the sine of 2 pi. Well, sine of 2 pi is equal to 0. Well, what about if I did 1/3? It would be the same thing. In this case, it would be the sine of 3 pi, which is equal to 0. If I did 1/4, it would be equal to 0. If I did 1/10, it would be equal to 0. Or even if I did 1 over 100, it would equal to 0. So basically, if I have this fraction where each time I'm putting in 1 over some natural number, what's going to happen is it's always going to end up being that natural number times pi, which sine of that will always be equal to 0. So if you looked at this, you might say, okay, well, it just seems like the answer is 0. And if we actually look at the visual of this, though, what does it look like is happening in the graph? Well, you can see that it's actually cycling between -1 and +1, -1, +1, -1, +1, and it's doing this over and over again. It's just we happen to be picking values where it was always hitting where our function f of x was equal to 0. And this is actually one of the issues you might run into if you're trying to do it numerically by picking numbers, because a lot of times when we're picking numbers, we will sort of arbitrarily pick some numbers a little bit away from that value that we're getting the limit for, and then we'll get closer and closer and closer and closer. But if you see behavior like this, well then, what does this mean? Does it mean that it converges to 0? No, not in this case. So in this case, because we know now looking at the image, the graph of this, that it's going from -1 to +1, we would have that this limit does not exist. So D and E does not exist because it's divergent, meaning that it doesn't converge on a specific value L. So now let's talk about our one-sided limits. So I've actually been kind of briefly mentioning this while kind of explaining limits as x approaches some value a, but let's formally define what these are now. So a left-hand limit is written as the limit as x approaches a with a little negative sign, f of x equals L. This means that our function f of x will approach that value L as x approaches a from the left side. That is to say that when x is less than a. The right-hand limit is written as the limit as x approaches a with a little plus on the function f of x will be equal to L. This means that our function f of x will approach L as x approaches a from the right. That is when x is greater than a. So there's one little typo in the slide, which is it should be x approaches a, like I said, not a approaches x like the slide shows. So for our next example, we're going to be looking at the limit as x approaches 0, and this will be 1 over x squared, if it exists. So the first thing we do is always just do a quick check. If I were to plug 0 into this, what would I get? I would get 0 squared at the denominator, which is 0. 1 over 0 is undefined, so therefore it can't be 0. So we're going to look at what happens as we approach from the left and from the right. Well, in this case, we have our x, we have our f of x. If I were to plug in plus or minus 1, right, because it's squared. So no matter what value I plug in for the negative or the positive, it's going to have the same outcome because this is an even function. If I plug in 2, it'd be 1 over 2 squared. If I plug in negative 2, it'd be 1 over negative 2 squared, which would still both be 1 over 4. So if I plug in 1 or negative 1 into this, I end up getting 1. If I were to plug in, right, because we want to get closer to 0. So if I plug in 0.5, then this would be 0.5 squared, which is 0.25. 1 divided by 0.25 is going to give me 4. If I plug in 0.2, I would get 25. If I plug in 0.1, I would get 100. So what's happening with this function as I'm approaching 0? Well, it appears that the value is getting bigger and bigger and bigger, and it's growing a lot faster as I get closer and closer to 0, which if then in that case, it looks like from the left and from the right, it approaches infinity. Now, there's going to be times where your left value from the left does not match what is occurring from the right. In this case, we would say that the limit does not exist. But in this case, a limit does exist. It's just that it diverges to positive infinity. No matter what value I plug in here, the closer I get to 0. So this would look something like this, right? I have this at 0. I know that whatever I have is going to go bigger and bigger and bigger, never touching at x equals 0. So it might look something like this. And we kind of briefly showed an example of something like this before, which was 1 over x squared. And here on the slide, you can just see an image of what I just drew on the board. So our vertical asymptote of f of x equals 1 over x squared is at x equals 1. We have an asymptote here, meaning that it will approach, but it can never actually touch that value. So therefore, even though we have that the limit approaches infinity, we would have for a specific limit that this does not exist. A limit L does not exist for limit as x approaches 0, 1 over x squared. Now looking at this example, you're going to see that we have a graph, but we don't have the actual equation for what the function is that defines this graph. So now normally I would actually have some sort of scale so you know exactly what these values are, but we're just going to kind of estimate it for the point of the example. So looking at this image here, we have that as we go to the left, it looks like it's kind of going down towards negative infinity. We're going to reach a certain point coming to the right where it's going to be included in the function, and then it's going to make a jump downward, but just not included. And then from there, it's going to increase until it hits a point that it cannot be, and then it's going to continue by going down and then approaching some possible value or maybe coming back up. I don't 100% know. But I'm not looking at the behavior as it goes to infinity. I want to look at it at specific points. So the first part is, what is the limit as x approaches 2 from the left on our function? So I'm guessing that's where that point is, where there's the dot and then the jump. So as it approaches from the left, it looks like it approaches some value of, I'm going to say 3 or 4. Okay, I had 3 for this example. What is the behavior then for when it approaches from the right? So the next one over, it says 2 from the left, but it should be from the right. Well, in this case, it looks like if I'm coming from the right, I'm probably approaching some value around 1. If I look at what is the function at x equals 2, right? So if I were to look at f of 2, I know that because the dot is at the top, that is what the value would be. So when I have f of 2, this should be equal to, in this case, 3. But what is the limit as I approach from the left and from the right? Well, they don't have a specific limit where both are approaching. So in this case, the limit does not exist. So if I just said, what is the limit as x approaches 2? The answer is does not exist because the left side limit, 3, does not equal the right side limit, 1. The next question is, what is the limit as x approaches 4, which is where that next hole is? Well, in this case, if the first one we were at was 3, I'm going to assume that this one I had written as 4, which means that from the left, I'm approaching and I'm getting 4. From the right, I'm also getting 4. So therefore, in this case, the limit would be equal to 4 because the limit from the left is equal to the limit from the right. So in this case, we get 4. Now, what is the value of the function at 4? Well, the fact that I have an open circle means that a value does not exist at x equals 4. So therefore, the answer would be does not exist. So in the previous example, we had a graph, but we didn't know what the function was that actually described it. So what we were doing is we were using the graph to try to say what the behavior was at specific points, at the limits for them as they approach specific points based on that function. Well, what about if we went the other direction? We now have the outcomes of different limits on our functions, and we want to draw a graph. So the first thing I'm going to do is I'm going to draw my x, y axes. So I've got my y, I've got my x. Now, before I begin, first thing I'm going to do is I'm going to quickly look through these to see where I'm actually going to be doing my limits to try to figure out where I need to kind of focus. So the first one looks like we're approaching limit as x equals 1. So I'm going to put a line right here to represent 1. The second limit, it looks like second and third limit, looks like I'm approaching 0 from the left and the right. So that means that I know something's going to happen here to the left and to the right of this value. And then we're going to look at as x goes to infinity and as x goes to negative infinity. So first thing, let's look at our limit as x approaches 1. So this line right here, f of x. And we have that it approaches infinity. Now notice this does not have a plus or minus next to it. This means that we are not taking the limit from the left or from the right. If a limit exists, so as the limit as x approaches 1, it means that both the left and the right are approaching the same value. And in this case, it looks like both are approaching infinity. So this means that we have an asymptote here where we have, from the left, it's approaching infinity. From the right, it's approaching infinity. Now, let's look at what's happening around 0. So we have the limit as x approaches 0 from the right. So if we look at 0 is here, as we're approaching from the right, that's this side. And we have that it's approaching negative infinity. So if I were to then make that happen, it looks something like this. So as it approaches 1, from the left, it's going to infinity. As it's approaching 0 from the right, it's approaching negative infinity. For my limit as x approaches infinity from the left, I also have that it is approaching negative infinity. My limit as x approaches infinity off to this direction is that it's going to go towards negative infinity. So that means that maybe it does something like this. I don't know exactly what the behavior is, right? We don't know the function. We don't know how fast it's decreasing. We don't know if it's hitting a certain point and going linear. We don't know if it's, doing something like this where it curves and then goes straight down. We don't know if it just kind of is sloping down. All I know is it's going towards negative infinity. And then my last one is, what about when my limit as x approaches negative infinity? Well, in this case, it says it's approaching 0, which means that as I go further and further to the left, I'm going to approach 0, but I'm never going to touch it. So now I have a graph that looks something like this. And looking at the slide, you can kind of see that it matches in general what I was drawing. Now, because we don't have these specific values, for example, as x approaches infinity, because I don't have the actual function, I don't know how it's decreasing to negative infinity. I just know that it is decreasing. So I drew it kind of slanted, whereas on the first graph I drew on the slide, I drew it more like what was on the other side of 1. Now let's formally define what a limit is. So we're going to say, let f be a function defined on some open interval that contains a number a, except possibly a itself, right? We looked at a case of this where we approach a, but we don't actually have the value a itself. Then the limit as x approaches a, so f of x equals L, if for every number epsilon is greater than 0, there's a corresponding delta that's greater than 0, such that if I have 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus the limit L is going to be less than that epsilon, which is the distance between the limit and the function. So what does this actually mean in practice? Well, what we're saying is this, is that let's say that we have some function, right? So let me draw my x and y axis. And let's say that I have some a right here. And my function is doing something. There might be a hole at a, there might not be. And pretty much what we're saying is that I have the limit as x approaches a on some function f of x, and this is equal to L. This is the limit. This is what I'm actually approaching, whether it's included or it's not. This is the value that I'm actually approaching from the left and from the right. What we're saying is that the distance from where my x value is, so this value here is x minus a, and then we're taking the absolute value of that, because whether we're approaching from the left or from the right, in this case, it would be same thing. It would be the negative of this. So this is actually going to be a minus x, and this would be x minus a. Either way, though, the distance whether we're coming from the left or the right, if I take the absolute value of that, so the distance from my actual, where I'm located on the x-axis, minus how far away, so basically this is the distance from A that I am. If this is greater than 0, meaning I'm not on A, but it's less than some delta, this delta just represents some threshold value, then this says that my function, because remember, wherever I am on x, this is going to be f of x. This value that's on my line is going to be where I'm actually located. So what this is saying is that the function f of L in this case, which is going to be, or f of x is going to be based on some distance between f of x and my value L, which is based on the limit it is. So we have f of x minus L, and again, I could be above, I could be below, depending on what the limit is and the direction of all that kind of stuff. So the absolute value of this will be less than some epsilon. So this is what the formal definition is of a limit, that basically that as I am away from A and I'm getting closer and closer, that there exists some threshold where I'm greater than 0, but I'm below some threshold value, which is represented by delta. And with that, I will have some distance that is a measurement of how far away I am at f of x from that limit that I'm approaching, which will be less than epsilon. And we'll use this if you were formally sort of proving different things about calculus. This is actually very important to that. Now, for this course, we're focusing more on the actual calculation and how to use calculus. So in this case, we won't really be looking at this unless we decide later on to look at more formal analysis. Let's say, though, that we actually did want to use it just for a really quick proof to show that the limit as x approaches 3, 4x minus 5 is equal to 7. So in this case, what we're saying is that we want to have some epsilon, which is greater than 0, right? Because we said that our absolute value of x minus a has to be between 0 and epsilon, meaning that our epsilon also has to be greater than 0. We have that our limit a, so this a equals 3, this is the limit that we're approaching. Our limit that we actually are getting when we approach a from the left and the right is equal to 7. Then what we need is for delta to be such that 0 less than the absolute value of x minus 3, because that's x minus a, we plug in 3 for our a, is less than delta. Then our absolute value of our f of x, 4x minus 5, minus the limit L, is less than that epsilon value. So remember, what we're saying is this, is that we had 0 is less than the absolute value of x minus a, is less than epsilon, and we had the absolute value of f of x minus my limit L is less than delta. And in this case, we have a is equal to 3, we have L is equal to 7, and we have f of x is equal to 4x minus 5, right? Because our original limit was the limit as x approaches 3, 4x minus 5 equals 7. So what we're doing is we're starting with the fact that we're going to be looking at the absolute value of this here, right? So we have 4x minus 5 minus L, which we said was 7. And we have that this is going to be less than some delta. So we start with the absolute value of 4x minus 5 minus 7, which is going to be absolute value of 4x minus 12 is less than delta. So now what we're going to do is we're going to focus on this here, and we're going to plug f of x in, so 4x minus 5 into f of x. We're going to plug 7 into L, and we will have that 4x minus 5 minus 7 for L is going to be less than our epsilon. So minus 5 minus 7 is going to be absolute value of 4x minus 12 is less than epsilon. Now the fact is both of these terms have a 4 in them, which the absolute value of 4 is just 4. So I can actually pull this 4 out of my absolute value. So this is going to be 4 is absolute value of x minus 3 is going to be less than epsilon. So then in this case, I'm going to divide by 4. So I'm going to get absolute value of x minus 3 is going to be less than epsilon over 4, which then going back to this here, we have x minus a, which we said a was equal to 3. So we have x minus 3, and the absolute value, which is this, is less than delta. So now going back, we have absolute value of x minus 3, which if you look up here, matches with this. Absolute value of x minus a. So we plugged in a is 3 based on what we had. So we have absolute value of x minus 3 is less than delta. Well, we have the absolute value of x minus 3 is less than epsilon over 4. So therefore, we have that delta is equal to epsilon over 4. Similarly, what if we wanted to show the limit that x approaches 0 from the right, square root of x is equal to 0. Now you might wonder, why are we specifically doing the limit from the right? Well, because if we plugged in values to the left of 0, that would be a negative, and we'd have a negative in the square root, in which case it would be complex issues. So we're just going to focus on the limit from the right. So we're going to start with the same stuff we did before. Well, in this case, our a is going to be equal to 0. Our L is going to also be 0. So then kind of doing what we did here, we have f of x is equal to the square root of x. So we're going to take the absolute value of f of x minus L. So we're going to take the absolute value of square root of x minus 0. And then this is going to be less than our epsilon e. Now, in this case, square root of x minus 0 is the same thing as just saying square root of x. So this is going to be equal to absolute value of square root of x is less than epsilon. Now, because we're taking the limit only from the right, this means that we can only have positive values. So the absolute value of square root of x is the same thing as just saying, in this case, the square root of x. So we have the square root of x is less than epsilon. So then if we wanted to isolate our x, we're going to square both sides. We would get that x is less than epsilon squared. So in this case, because we're looking at this, our absolute value of x minus a, which we just said is equal to x in this case, because with the steps we just did here, this is going to be less than our delta. Well, this means that our delta is equal to epsilon squared. Now, we're not going to do much more with this. I just wanted to kind of briefly show you the idea behind the formal definition of a limit, but we're going to be mostly focusing on, going forward, applications, how to solve them, different rules, and things like that, and then build out till we get to derivatives, integration, things like that. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.